Swayam Prabha. Digital India. Educated India.
I welcome you all to the lecture 3 of week 10. In week 10, we are studying various control walls and the graphical representation. In this lecture, we will have an elaborate discussion on the graphical representation of various elements which are used in a typical hydraulic system. So, let us look at the outline of the lecture. At start of the lecture, we will have a discussion on the purpose, why it is needed to have the graphical representation. What is the methodology of representing a hydraulic system by using variety of elements. There are a lot of elements we have seen till now, and we will see how to represent them in a proper way, in a standard way. So, these elements are pumps, valves, actuators and motors. So, let us begin the lecture 3 of week 10. Till now, we have seen various elements of hydraulic system. We have seen pumps, we have seen various valves, we have seen the variety of actuators such as the hydraulic cylinders, piston cylinder arrangements. The valves, the actuators, pumps and electric motors, they do combine and give us a hydraulic power pack. Such hydraulic power packs are used in the industry for a variety of applications. In a typical automation industry, there may be many applications of hydraulic system and they are integrated to each other. Some of the applications are interdependent. So when we design a hydraulic system, we have to first select the appropriate elements for the hydraulic system, then we have to assemble them together. So during the process of selection and assembly, we have to communicate the hydraulic circuits which are designed by the designer to the process planner or the purchase engineer. And it is also to be communicated to the shop floor engineers, those who are doing the actual assembly operation. In this process, there is a lot of communication that to be carried out, and as we have seen, the construction of the hydraulic elements is very complex. The walls are complicated and some of the walls they do have the similar construction. So there may be chances of having the ambiguity, there may be chances of having the confusion during the communication based on the actual figure, the real picture of the drawing. It's very tedious, it's very cumbersome for communication with this. So therefore, the graphical representation of these elements have been developed for the simplification, for the ease in communication of the complicated hydraulic circuits. The graphical representation is also very much helpful for the comprehension of the hydraulic circuit, for the better understanding of the hydraulic circuit. Based upon the graphical representation, various drawings can be created, various circuits can be created which are very similar to the electrical circuits or the mechanical circuits or mechanical systems. The graphical symbols are thus used to indicate the various elements that are used in a hydraulic circuit. The primary function of the graphical symbol is to specify the function of that element. The primary purpose of representing the elements graphically is to specify the function of the element without indicating the design of the element, without indicating the physical appearance or the internal construction of that hydraulic system element. However, these graphical symbols or graphical representation should indicate the actuation method. What kind of actuation method is being applied? Is it the mechanical actuation or pneumatic actuation or pilot actuation, hydraulic actuation or electromechanical actuation? The graphical symbols should represent the direction of flow of fluid, which is very essential. Otherwise, it is meaningless to just put the symbols in the circuitry without giving the direction of the flow of fluid. The designation of the ports. So we have seen various types of external openings are there to the walls, and these ports are to be designated. So this may be the pressure port or the application port, or they may be the tank port or the sump port. To standardize this communication, to standardize the convention of providing the graphical symbols, various guidelines are available, and these guidelines can be seen on your screen. These are DIN 24300, BS 2917, ISO 1219. The newer guideline or newer standard is the ISO 5599, and many such standards are available. These standards are being employed by, these standards are being practiced by the practicing engineers in the industry. Therefore, it is very much essential for the budding engineers, for the students of the automation engineering or the manufacturing engineering should know how to represent properly a typical hydraulic element. What characteristics of the graphical symbols? The characteristics are as follows. The graphical symbols are designating, they are defining the function of the element, they are defining the actuation and the return method. The symbols are providing the information about the number of connections to that, to a particular element or to a particular hydraulic system. The symbols are also providing the information about the switching positions. So how many positions are there? It may be a 2-position wall, or it may be 3-position, or the 4-position wall. Based upon this, we can communicate in a better way about the operation of the hydraulic system. The graphical symbols are also providing information about the operating principle of that element. So overall, we can say that the graphical symbols are providing the simplified representation of flow of path of the fluid. It may be hydraulic fluid or it may be the compressed air in pneumatic systems. But what it is not indicating, what the symbols are not representing. So these characteristics are the size and dimensions of the component. The sizes may be very large or very small. Huge sizes of the components such as the motors, tanks or piston cylinder arrangement, to draw them on the paper it's very difficult. So the size and the dimensions are not being represented on the paper or in the digital drawings which we are using commonly nowadays. The graphical representation does not provide the information about the manufacturer or the method of construction of the element. It also doesn't indicate the cost of that particular element. It also not representing the operation of the port. The internal construction of the port, internal operation of the port is also not been communicated by the symbols. So any physical details about the element is not specified in the symbol. Now let us look at what are the port designations as per the ISO 5599. So on your screen you can see the various ports that are used in a typical hydraulic system. As per ISO 5599 or as per the various designation systems, we can use a letter or we can use the numbers as well. So particularly the ISO 5599 is providing the facility to designate the ports by using the numbers. Or in general, we are using the letters such as the letter P for the pressure port or the power port, or you can call that as the pump port as well. However, in number system, number 1 has been designated to the pressure port. There are various working ports which we have seen. The working ports are the actuation ports. The port A is connected to the extension requirement of the piston cylinder arrangement, and the B may be connected for the retraction or the contraction of the piston cylinder arrangement. So the number 4 is assigned to port A and number 2 is assigned to port B. We have seen in our previous slides that the tank or the sump is the integral part of a hydraulic power pack. So to designate the tank or the sump, the letter T is used, and in number system it may be 3 or 5. We are using the external fluid, we are using external air, compressed air to actuate the valves, to operate the valves. So these are called as the pilot ports. So pilot ports are designated by using the letters Z or Y or X, and the numbers can be seen on your screen. The hydraulic pump is basically designated by using a circle, and that circle is having a filled in triangle. The triangle in this format, which is filled in, that is designating the hydraulic pump. When only one triangle is provided, the meaning is that this is the one direction pump. When two triangles are provided in opposite direction, that is the meaning is that it is a two direction of the pump. With two parallel lines is designating that the displacement volume is constant. With constant displacement volume, the pump is working. But many pumps are having the variable displacement. The displacement is changing as per the requirement. To represent that variable displacement, we are using an arrow. The arrow is placed in this format. As the arrow is there, we can easily say that the pump which is represented is having the variable displacement. We can use the representation for the actuators as well, and the hydraulic motor is a rotary actuator. The hydraulic motor is working on the principle that we are using the hydraulic energy, and that hydraulic energy will be converted into the rotational energy, and that rotational energy or rotational movement will be utilized for our intended application. The hydraulic motor is also represented by a circle. It is also having a triangle, but the orientation of the triangle is exactly opposite to the orientation of triangle that we have seen for the hydraulic pump. The triangle is filled in triangle, so when only one triangle is represented, the meaning is that the motor is allowing to have only one direction of the rotation. The two parallel lines are designating the constant displacement volume. If we are using two field-in triangles for the hydraulic motor, that means it is providing us the two-way direction of the rotation. And the two parallel lines for the second schematic representation is giving us the information that it is also the constant displacement volume hydraulic motor. Similar to hydraulic pump, if we want to have the variable displacement that to be accommodated, a variable displacement that to be provided, so then we are putting an arrow, as you can see on your screen. The meaning of the arrow is that the motor is working with the variable displacement. Now let us study how to represent a typical valve. A valve is represented by a square for each of its switching positions. A typical two-position valve can be represented by using two squares. So let us draw the two squares. So this is position B and position A. So this is two position valve. So we can have a three position valve as well. For that purpose, we may need to utilize three squares. So this is position B, position A, position A, and the O position. So O is basically used to designate the central or the neutral position. So O is the central, or you can call this as the neutral position. Now to these positions, we are adding the ports, we are adding the actuation information. Let us see if we are having a typical. Now here we are designating the ports. Consider this two position valve is having the four ports. The port P is designated the pressure port. The port T is designated the tank port, and it is having two application ports A and B. So the vertical lines outside the square are representing the ports, and the letters or the numbers which are designated here are representing the ports. So the P is 1. Now if these positions are also to be added the information about the actuation. Now let us understand how to represent, how to designate the valves. Now to understand the graphical representation of valves, let us take an example. How to control the movements of a double acting cylinder. So let us consider a double acting cylinder, and we have to control its operation by using a valve. So to communicate this information to the shop floor, how we will carry out the representation. The double acting cylinder is represented by using a simple T, that is the piston which is located inside a cylinder. Now to actuate this means what? We are applying the fluid energy at the top center. There would be extension of the cylinder, the piston will come out. And the pressurized fluid which is at the rod side, that to be moved to the tank. Now in the next position, we need to have an arrangement which is making us possible for the retraction of the cylinder. So for that purpose, we have to have the pressurized fluid flow at the rod side, and so that the cylinder will get retracted. But the pressurized fluid which is there at the top side, that to be taken to the tank side. So for that purpose, we need a valve. We need the two position, that is the extension position and the retraction position. So let us draw a two position valve. We need to have a two position valve. Now the normal position we are considering here is the contraction or the retraction of the cylinder. So the retraction of the cylinder, as I mentioned, that we have to have the pressurized fluid at the rod side. So let us connect this to the rod side. So the valve should have a port, application port A, which is connected to the rod side. So let us draw this as port A, which is connected to the rod side. And we are having another purpose, that is the discharge of the pressurized fluid at the top of the piston, that to be taken out to the tank. So for that purpose, we need to have another port. This is another port that is needed, and this is the port B. So port A for application of the pressurized fluid at the rod side, and port B is to take the fluid back to the tank. To provide the pressurized fluid, we need a pressure port, that is P, and to take the pressurized fluid from the piston cylinder arrangement back to the tank, we need a port T. Now for this position, we have to designate the direction of fluid flow as well. So here we are representing, as per the convention, the number of positions are shown, the number of ports are shown, the connections are drawn, but we have to show the direction of fluid flow. So for this position, the direction of fluid flow is from P to A. So let us draw P to A, and the fluid is getting to the tank from B to T. So B to T. But the valve is operating on what actuation? So this particular position has been maintained by a spring. Spring is designated by using a zigzag lines. So these zigzag lines are representing the spring. The spring is controlling this particular position. This is the normal position of this particular valve. Now, as I mentioned, I have to now extend the piston cylinder arrangement. I have to extend the cylinder. So for that purpose, I need to provide the pressurized fluid from P to B, and I have to get back pressurized fluid from the rod side to the tank. So the connection are now to be from P to B and A to T. Thus the initial position will now be changed to the next position. So in the next position, P is to be connected to B and the A is to be connected to T. So in this case, we are not rewriting the A, B, P, T for the next position. It is understood that this point is P, this point is T, this port is A, this port is B. Only we are providing the direction of movement of the fluid for the next position. But we need to provide how this position is getting achieved, how this position is getting actuated. So for that purpose, let us consider if we are using a push button. So when we apply the energy, when we apply the force at the push button, the position from the spring operated port connection to the opposite connections will be achieved. So when somebody will look at and will try to comprehend this particular circuitry, simple circuitry, then it is very easy to understand that the wall is having two positions, it is having four number of ports. The default position is P to A and B to T, that is the contraction of the double acting cylinder, and that is controlled by using a spring. So to change the position or to change the connections of the ports, we are using a push button arrangement. As we actuate, as we push the button here, the connections are getting in an opposite direction. The P is getting connected to B and A will get connected to T. So in this way, by drawing a simple graphical representation, we can communicate very complex phenomena, very complex operations of the hydraulic systems. Now let us see how can we represent the infinite position wall. Infinite position wall is nothing but a wall which is providing a number of position. So in general, as we have seen that the walls are providing only two or three, a finite number of position. In this case, it is providing the infinite number of position. So we have to just operate the wall, we have to operate the stem of the wall, and we can have a variety of positions. So that infinite number of position wall can be designated by using a simple square, and in that square we are using an arrow. So this is the arrow which is placed in the square, and it is showing the line of application of the fluid. This is the simple designation of the infinite position wall. Now if we want to put the actuation symbols with actuating symbols or with actuation symbols, it can be designated as the square with the arrow, the line of fluid flow, and now we have to put the actuation. Normally the infinite position wall is closed, and that the closed position is being controlled by a spring. To open this particular wall, we are using a pilot pressure. So to designate the actuation by pilot pressure, we are using the dotted lines. The pilot pressure is applied. And when the pilot pressure or the external pressure is applied, the wall is getting open. Opening of the wall due to the pilot pressure. Now let us see how it is working in the practice. To understand that, let us draw a flow line. So here we are getting the pressurized fluid from pump, and it is going to the system, to the load or to the application. So inside this line we are using this infinite position wall. So we have taken a branch of the fluid, and that branch of the fluid is passed through this wall. So as you know that the normal position of the wall is closed due to the spring. The pressure is applied by the spring, But when the system pressure is increased, the load is very high, it is blocked, there is no need of the, the pressurized fluid from the pump continuously to the system. It is not essential. Already the load, already the pressure at the system is very high. So due to the increase in pressure at the application, at the load, at the system, we need to now relieve the pressure. We have to reduce the pressure of this particular flow line. To carry out this, we are using a pilot pressure which is part of the system pressure itself. We are getting a branch of flow line from the system, and that is connected to the wall itself. So this dotted line is the pilot pressure, and that pilot pressure is part of the system itself. Now when this pilot pressure is more than the cracking pressure of the wall, when the pilot pressure is more than the cracking pressure, the wall will get open, and after opening up that wall, it will pass that excessive pressurized fluid to the tank or the sump. So how to decide the cracking pressure? How to provide the cracking pressure? So for that purpose, we have to use the screw. The screw based arrangement is utilized, and that has been shown by using an arrow which is put over the spring. So meaning of that arrow over the spring is that we are setting the pressure. We can set the pressure here, setting up the pressure by using the screw arrangement. So in this way, a simple infinite position wall is converted into a pressure relief wall. So by default, it is closed. The pressure of the spring has been set up by a screw. When the system pressure is more, when the load pressure is more, and we have to safeguard the entire system from the damage, we are using the pilot pressure, a branch of the pressure, branch of the flow line from the system itself, which is operating the wall, and as the pilot pressure is more than the cracking pressure of the wall will get open and it will send that fluid to the tank. Let us draw the graphical representation of the check valve, a very useful element of a hydraulic power pack, that is check valve. We have seen the working of the check valve in our previous lecture itself. The check valve is having a ball and a spring arrangement, and it is not allowing the fluid in one of the directions. But when the applied pressure is more than the cracking pressure of the spring, then the fluid will be allowed to pass from the other direction. So in this case, the fluid is passed, or it is allowed to pass from the pump to the application line, but it is not allowed to pass from the application line to the pump. So this is the pump port, and this is the system port. So to show the operation of this valve, let us draw two squares. So at normal position, the flow is blocked. So let us consider the flow is there inside the valve, but it is blocked. There is no pressurized fluid is passing through the wall at its default position. The free flow is from left to right, however it is blocked, and that blocking is due to the spring. So due to the spring we are blocking the flow of fluid. It's not only the spring, it is due to the system pressure itself. The system is applying the pressure on this side. Due to that as well there is blocking. So to designate that system pressure we are showing the dotted lines. So this is the default position of the check wall. But when the inlet pressure is more than the cracking pressure, so let us consider a branch of the free flow is used as an actuation element itself. When the inlet pressure, which is designated by using a dotted line, if this inlet pressure is more than the cracking pressure, is more than the spring pressure here, then there is flow of fluid is possible from the direction shown over here. From left to right, the flow of fluid is possible when the inlet pressure is more than the cracking pressure. So in this way, the check wall has been represented. Though the construction of the check wall is very simple, its operation is also very simple, but the representation is very complex. So in conventional way, we are representing this flow wall by using an arrow and a circle, and there is the flow line. So in this way, the conventionally we are representing the check wall. So this is the functional symbol. This is functional symbol, and this is the conventional symbol. So it is very tedious every now and then to use such a complex representation in the hydraulic circuit. It will consume a lot of space, and it may lead to the confusion as well. So therefore we are using a simplified representation in this way. So this arrow designates that there is a blockage, and on left to right side the flow is allowed. So this is the free flow is from left to right is allowed. However, from right to left the flow is blocked. One more example we will study for the representation of the walls. On your screen you can see a 4 by 3 wave wall. This is a 4 by 3 wave wall. We have seen the meaning of the 4 by 3 wave wall in our previous class. So it is having 4 ports. There are 4 ports and 3 positions. The default position is seen on your screen, that is the blocking, it's a holding position. The port A is blocked, the port B is also blocked, and they are at hold position. So port T, there is no fluid is coming to the port T. The port through port P, through pressure port as well, no fluid is going to the port T and port A and B. So by default, or the center position is the hold position, or the neutral position is the hold position. So here we are having the 2 ports. So these are the 2 ports which are blocked, port A and port B, both of them are blocked. From port P there is no fluid is going, so we can consider this also the block in block position, port P, and the tank is also in a block position. But let us consider that when we give the movement from the right towards the left, so what will happen? If I move the spool from right to left, so we are changing the position of the spool. So let us add the square. So if I change the position of the spool from right to the left, what will happen? When the spool is moving from right to left, port P will be connected to port A and port B will connected to tank port T. So P is giving the pressurized fluid to port A and the pressurized fluid from B is coming back to P. So here what is happening? P is connected to A and B will be connected to the T. So for the first position, so I can draw here the P will be connected to the A. Simply I will just draw an arrow indicating that P is connected to A and B is connected to T. Consider we are giving spool movement from left to right. So when we are giving the movement from left to right, we are having one more position here. So to draw that, we are using one more square. Now when we are pushing the spool from left to right, power port will be connected to B and application port A will connected to port tank T. So here P will be connected to application port B and A will be connected to the tank port T. P to B, so P to B, just draw, right, and from A to T, A. So this is the representation of 4x3 wave wall. Now here you can add the actuation. So let us consider that the wall movements are actuated by the solenoid. By using the solenoid, we are actuating the walls. These are the solenoid actuation. So in a similar way, we can represent various DCVs, that is a directional control wall. So on your screen you can see a 2x2 wave wall. So it is having two positions and there are two ports. So by default it is blocked. So when we are actuating, the port 1 is getting connected to port 2. So it is a two closed ports in the neutral position and the flow will occur when we are actuating the wall. Similarly, we can have the representation of 3x2 wave wall. So here the 3 means number of ports are 3. So 1, 2, 3 number of ports and there are two positions, position number 1 and position number 2. In the first position, the flow is taking place to the cylinder. Flow is taking place to the cylinder. So from port 1, that is a pressure port, it is giving to the piston cylinder arrangement and the tank port is blocked. So in the second position, the flow is taking place from the cylinder back to the tank. So this is in general the working of a single acting cylinder by using 3x2 wave wall, 3 ports, 2 position wave wall. We can have the understanding of the 4x2 wave wall. You just observe the 4x2 wave wall. So the 4 is the number of ports and 2 is number of positions. The port 1, port 2, port 3 and port 4. Port 1 is the pressure port, port 3 is the tank port, 2 and 4 are the application ports. The 4x2 way valve is generally used to actuate the double acting cylinder. By default, or the neutral position is allowing the ports that are open. So 1 is connected to 4 and 2 is connected to 3. So we are allowing the pressurized fluid that to flow inside the double acting cylinder. From the rod side end, the fluid is coming back to the tank. So when we actuate this valve, the connections are getting reversed. So 1 is getting connected to 2 and 4 is connected to 3. In similar way, we can also have a 4x3 way valve, which we have already seen in our previous slide. The designation can be seen on your screen. So there are 2 open positions, 1 closed neutral position. There are various ways to represent the actuation methods. Consider a manual actuation method. So if you want to control the valve by using the manual actuation, so we are using a simple symbol. So the symbol is having 2 parallel lines and a vertical line. So that is designating it's a manually operated. If we are using this kind of arrangement, it is called as the push button actuation. So when we want to give the push button, so we are using a semicircular representation with 2 parallel lines, a bar and a push button, a button which is attached to the bar. When we are trying to represent the lever, we are using a little inclined line with a circle to represent the lever based actuation. The mechanical actuations can be represented as like the detent lever actuation. So detent is the locking mechanism. So by the detent we can have the facility to hold the position of the valve. For that purpose, detent is a mechanical element which is having the various the slots, and that slots are utilized to lock the valve in its intended position. We can have the roller lever actuation. So the roller lever can be represented by a circle with concentric field in circle. This is representing the solenoid actuation. This is the solenoid actuation. We are using a rectangle and an inclined line. The solenoid actuation, as we know that it is the electromechanical actuation. The springs are represented by using a zigzag line, and we can also utilize the pneumatic based actuation. When we are using the compressed air to operate the valves, we are using arrow. We are using an arrow which is not filled in arrow, so empty arrow, and that is designating the direct pneumatic actuation. The check valve is represented by using this symbol. Already we have seen the meaning of this symbol and how it has been derived. The check valve is allowing the flow in only one direction and it is blocking the flow in the other direction. So we can have the spring loaded check valve as well. So when the check valve is spring loaded, we are using a zigzag line as shown on your screen. The flow control valve can be represented by using a rectangle, and there are 2 curves. These 2 curves are represented in this way, and it is having an arrow. So arrow is representing the variable displacement, the variable flow of the fluid through the flow control valve. The flow control valve with one-way adjustment can be shown by using the diagram on your screen. Here we are having 2 arcs which are represented in this way and an arrow, and there is a check valve. So what is the meaning of with one-way adjustment? So it is allowing the controlled flow in one direction and the free flow in other direction. It is allowing the flow of the fluid in a free way from left to right through the check valve against the spring pressure in this direction, and in the reverse way the flow control valve is taking care. The unloading valve, which we have seen in our previous lecture, can be represented by using a square and a fluid flow line. By default the unloading valve is closed. The closed valve due to the spring action is represented by a spring, a zigzag line over here. So when the external pressure we are applying, external fluid pressure, the pilot pressure is applied to safeguard the system, then the valve will open and it will allow the pressurized fluid, the excess pressurized fluid, to pass through the valve, and that will send to the tank. So in this way the unloading valve is controlling the pressure, and that has been designated by using a simple representation. The hydraulic actuators such as the single acting cylinder and the double acting cylinder can be seen on your screen. So the single acting cylinder can be seen, it is having the piston and the rod. The rod and the piston are having a spring. So when we are applied the hydraulic pressure at the top side of the piston, it will be extended. The cylinder will be extended. However, restoring of the cylinder will be done by the spring force itself. In double acting cylinder, we are using two ports. In single acting cylinder, there is only one port. So in double acting cylinder, as you can notice, there is a pressure port at the top side of the piston, and there is a one more port at the other side of the piston movement. So the double acting cylinder is based upon the extension and retraction both by using the pneumatic or the hydraulic force. However, in the single acting cylinder, the retraction by taking place the spring force, but the extension would be carried out by the hydraulic fluid only, the pressurized hydraulic fluid. In the industry, a lot of hydraulic fluids are being utilized, and as we know that the hydraulic fluid is the medium through which we are transferring the power to the hydraulic machinery. So in general, water is the best hydraulic fluid, but the flash point of the water is very less. It will get evaporated at a low temperature, comparatively low temperature. Due to the friction inside the system pressure may increase, the temperature will also increase, and that may lead to the boiling of the water, which is leading to the cavitation problem and the failure of the device itself. The viscosity of the water is also a concern. The viscosity of the water is low, so we need a little high viscous fluid. For that purpose, the mineral oils are the best choice to be used as the hydraulic fluid. The primary function of the hydraulic fluid is to transmit the power. We have to transmit the power from the pump to the designated load or the desired application. There are certain properties that an ideal hydraulic fluid should have. The fundamental property is that it should be non-compressible. It should not compress, so that it will transmit the power efficiently. It should not form any foam during the operation. It must be less volatile. The ideal hydraulic fluid should have very good thermal capacity. The heat capacity should high, and it should have good thermal conductivity. If the conductivity is low, it will get heated up, and that hot hydraulic fluid will lead to the failure of the system. It will damage the system. The hydraulic fluid should have sufficient thermal and oxidative stability. The fluid should be stable enough. It should have the hydrolytic stability as well. The fluid must be clean and it can be easily filtered. The hydraulic fluid should provide the anti-wear characteristic. It should provide good lubricating characteristic. It should be non-corrosive. Generally, the hydraulic fluids are corroding the mechanical elements, the ferrous elements of the system, and we need to continuously monitor the condition of the hydraulic elements. Due to the corrosion, the system strength will get reduced and that may lead to the failure of the system. The corrosion is a concern in the hydraulic fluid based systems. The hydraulic fluid should provide minimum possible the corrosion inside the system. The hydraulic fluid should be low toxic. We are using the hydraulic systems in presence of the human beings. The fluid will be handled by the human beings. So it should not harm the health of the human beings. It should be less toxic. It can be easily decomposed. If it is a biodegradable, that would be the best, the hydraulic fluid. It should have the resistance capability to the fire and it should have even the radiation resistance as well. The fluid material, as I mentioned, is the water. Earlier when the hydraulic system started, people started using the water, but later they changed the water or they replaced the water as base stock to the mineral oil. The mineral oil is having inherent lubrication properties and we can use the mineral oil at the temperatures above the boiling point of the water. So most of the hydraulic fluids are based on the mineral oil as base stocks. So natural oils such as the canola oil can also be used as the base stock. The canola oil or the vegetable oils are having the best characteristics as they are biodegradable. To improve the performance of the hydraulic fluids, certain elements are being added in the hydraulic systems and these contains various chemical compounds. So these are the butanol, esters, polyalkyl glycols and various chemicals are added to get the required properties as I mentioned in the previous slides. Even we are adding the silicons, corrosion inhibitors, anti-erosion additives and many such elements are added to improve the performance of the hydraulic fluid. Well, let me summarize the lecture 3 of week 10. In this lecture, we have seen the graphical representation of variety of elements which are required to build a hydraulic circuitry. We discussed the importance of graphical representation. We have seen what are the aims and methodologies to represent these elements. We have seen typical elements representations such as pumps, valves, actuators and motors.